All right, so you know how much we love diving into the latest and greatest in AI, and you sent over some material on this really wild new approach to language models, and honestly, I gotta say, I think this might be a pretty big deal.
Yeah, it's definitely something that's got people talking in the field, and for good reason. We've all been so focused on these large language models, these LLMs that have been making headlines.
Right, the ones that are amazing at generating text, composing music, even coding.
Exactly. But they all rely on this basic idea of processing language at the token level, basically word by word or even parts of words. And this new research is proposing something totally different.
Large concept models, or LCMs.
Yep, LCMs. And they aim to process information not in terms of individual words, but in terms of, well, concepts like ideas.
Okay, so right off the bat, that sounds a lot closer to how we humans think, right? I mean, we don't think in individual words, we think in ideas and whole chunks of meaning.
Exactly, and that's a big part of the motivation behind this research. The idea is that if we can build AI models that operate at this higher level of abstraction, they might be able to do things the current LLMs struggle with.
Like what? Give me some examples.
Well, think about things like reasoning, planning, really understanding the nuances of a complex argument, or maintaining a coherent train of thought over a long piece of writing. These are things that humans are pretty good at, but LLMs, even the really big ones, still find challenging.
So the thinking is that by focusing on concepts rather than just words, LCMs could potentially overcome some of these limitations.
Yeah.
Okay, so I'm definitely intrigued. Let's dive into the details. Where do we even begin with this whole concept thing? Like, how do you even define a concept in a way that an AI can work with?
That's the really clever part. In this study, the researchers define a concept as the underlying meaning of a sentence.
Okay, so not just a single word, but a whole sentence as a unit of meaning.
Right, and the key here is that this meaning is language agnostic. So it doesn't matter if the sentence is in English, Spanish, French, or any other language. The concept, the core idea being conveyed, is the same.
So it's like if you see a picture of a cat, you immediately understand what a cat is, right? That understanding isn't tied to the word cat itself, whether it's cat in English or gato in Spanish or chat in French, right? It's something deeper than the specific word.
Exactly. It's the underlying concept of catness. And LCMs are trying to capture that same level of meaning, but for entire sentences. They're not looking at the surface form of the words. They're looking at the deeper semantic representation.
Okay, so that's a pretty big conceptual leap. So how do they actually get these AI models to work with these abstract concepts?
Well, they use a system called Sonar, which is a really fascinating piece of technology in its own right. Essentially, Sonar is a sentence embedding space, which means it can take a sentence, regardless of the language it's in, and turn it into a fixed size vector, a kind of numerical representation of that sentence's meaning.
And the Sonar system, is this something they developed specifically for this research on LCMs?
No, actually, Sonar already existed.
Yeah.
It's been used for other natural language processing tasks, and what's really cool about it is that it's been trained on a massive data set of text and speech in a ton of different languages.
Like how many languages are we talking about here?
Up to 200 for text input and output, and 76 for speech input.
Wow. That's way more than most language models can handle.
Right. And the really mind-blowing part is that they've even got some preliminary work done on using Sonar with American Sign Language.
ASL. So we're not even talking about spoken language anymore. We're talking about capturing the meaning of visual gestures.
Exactly. It really highlights just how flexible this concept-based approach could be.
Okay, so Sonar seems to be the key ingredient here. It takes sentences and turns them into these language-agnostic meaning vectors, but how did they actually build this Sonar thing to be so universally understanding across all these different languages and modalities?
It's a really sophisticated system that leverages several different techniques. They use machine translation, which is basically training a model to translate between languages. They also use something called denoising autoencoding, which involves corrupting the input in various ways and then training a model to reconstruct the original input. And the loss function they used was mean squared error, or MSE, at the embedding bottleneck, which basically means that they were trying to minimize the difference between the embedding of the original sentence and the embedding of the reconstructed sentence.
So by training on all these different tasks across all these different languages and modalities, they were able to create this kind of universal translator, a system that can capture the meaning of a sentence regardless of how it's expressed.
Right, and for LCMs, the really important thing is that the Sonar encoder and decoder, the parts that turn the input into embeddings and back into text, are kept frozen during the LCM training process.
Frozen?
Yeah, they don't change. The idea is that sonar provides this stable foundation of meaning, and the LCMs are then trained to work within that space of meaning.
Okay, I'm starting to get the bigger picture here. We have sonar turning sentences into these meaning chunks, but how do the LCMs themselves actually work with these concepts?
It's actually pretty straightforward. Let's say you have a document you want the LCM to process. You first break the document down into individual sentences.
Okay, sentence segmentation. Makes sense.
Right. Then each sentence is fed into sonar, which generates a concept embedding for that sentence.
So we have a sequence of these meaning vectors, one for each sentence in the document.
Exactly. And that sequence is then fed into the LCM, which is typically a type of neural network. The LCM processes this sequence of concept embeddings and learns to predict the next concept embedding in the sequence.
So it's kind of like those next word prediction models, but instead of predicting words, it's predicting concepts, whole chunks of meaning.
Exactly. And then once the LCM has generated a sequence of predicted concept embeddings, those embeddings are fed back into sonar, which decodes them back into text or potentially speech, depending on the task.
Wow. So the LCM itself never actually sees the words or hears the sounds, right? It's purely operating in this abstract realm of concepts.
Right, which is why it has the potential to be so flexible and powerful. It's not tied to any specific language or modality.
So in theory, you could train an LCM on a massive data set of English text and then use it to process and generate text in any of the other 200 languages that Sonar supports without any additional training.
Exactly, and that's what the researchers call zero-shot generalization, is one of the most exciting potential benefits of this concept-based approach.
Wow, okay. That's pretty mind-blowing. So we've got this big advantage in terms of language and modality independence, but what are some of the other benefits that the researchers are seeing with these LCMs compared to traditional LLMs?
Well, one key advantage is this ability to reason at a more abstract level, as we talked about earlier. Because they're dealing with concepts, they can focus on the underlying logic and flow of ideas rather than getting bogged down in the specific wording. And this ability to reason at a higher level could lead to better performance on tasks that require more than just pattern recognition.
Interesting. So they might be better at things like problem solving, decision making, or even creative writing.
Exactly. And because they can be trained on data from so many different languages and modalities, there's also the potential for more scalable and unbiased learning.
That makes sense. The more diverse the training data, the less likely the model is to be biased towards any particular language or culture.
Right. Plus, the researchers believe that LCMs might produce output that has a more natural hierarchical structure because they're working with sentences as the basic unit of meaning, which could potentially lead to better readability and coherence in long-form text generation.
Makes sense. Instead of just stringing words together, they're building up a kind of outline of concepts, which could make the overall structure of the text more logical and easier to follow.
Exactly, and because they operate on these shorter sequences of sentences, rather than the very long sequences of tokens that LLMs typically process, they might also be more efficient at handling long contexts, which is a known issue with many current LLMs.
Yeah, the longer the text you feed into an LLM, the more computationally expensive it becomes. But with LCMs, you're essentially summarizing the text into these shorter concept sequences, which could make them much more scalable for tasks involving really long documents.
Right. And another big advantage is modularity.
Okay, what do you mean by that?
Well, because the concept encoders and decoders, like Sonar, are separate from the core LCM, they can be developed and improved independently, and new languages or modalities can be added without having to retrain the entire LCM, which makes the system much more flexible and extensible.
So you could imagine a future where there are all sorts of specialized concept encoders and decoders for different domains or tasks, and you could just plug them into an existing LCM to adapt it to your specific needs.
Exactly. And that's pretty powerful.
Okay, so I'm seeing a lot of potential upsides here. But training these LCMs can't be easy, right? How do they even get started?
One of the big initial challenges is data preparation. Before you can even start training an LCM, you need to break down your text data into meaningful individual sentences, which is called sentence segmentation. And this might seem simple, but it's actually quite tricky when you're dealing with a massive multilingual data set.
Why is that? I mean, can't you just look for periods and question marks?
Not really. Different languages have different rules for punctuation, and some languages don't even use spaces between words. Plus, you have to account for things like abbreviations, acronyms, and other special cases.
So they had to come up with some clever ways to segment the text accurately.
Exactly. They experimented with different existing techniques for sentence segmentation, including 𝒂𝒐, which is a popular natural language processing library, and another tool called segment any text, or CT, which is a more general-purpose segmentation tool. And what's interesting is that they found that a modified version of T, which they called 𝒂𝒂𝒏𝒈𝒆, performs slightly better in terms of preserving meaning during the encoding and decoding process.
𝒂𝒂𝒏𝒈𝒆, how did they modify it?
They basically put a cap on the maximum length of a sentence, which seems to have helped to prevent really long and complex sentences from losing too much of their meaning when they were compressed into these fixed-size concept embeddings.
So there's this kind of sweet spot in terms of sentence length. Too short, and you might lose some of the nuance. Too long, and the meaning might get muddled.
Exactly.
Okay, so data preparation is a key step. What about the actual training of the LCMs? What kinds of experiments did they run, and what were some of the most interesting results?
Well, they used a variety of metrics to evaluate how well the pre-trained LCMs could predict the next concept in the sequence, which is essentially a measure of how well they're understanding the relationships between these concepts. They looked at things like the L2 distance, which is a measure of how far apart two vectors are in the embedding space. They also looked at the round-trip L2 distance, which is a measure of how well a predicted embedding could be decoded back into text and then re-encoded back into the original embedding. And they used a metric called contrastive accuracy, which measures how well the model can distinguish between the correct next concept and other random concepts. They also looked at paraphrasing and mutual information.
So they were really trying to get a comprehensive view of how well these LCMs were learning to understand and predict concepts.
Right, and they explored a few different approaches to training the LCM itself. They had a baseline model, which they called base LCM, which just used a straightforward mean squared error loss to predict the next concept embedding. Then they experimented with using diffusion models, which are a type of generative model that's been really successful in image generation.
Diffusion models for language, that's interesting.
Yeah, it's a relatively new approach, and the basic idea is that you start with a real concept embedding, and then you gradually add noise to it until it's just random noise. Then you train a model to reverse this process, to learn how to denoise the noisy embedding back into the original concept embedding. And by learning to do this denoising process, the model learns how to generate new concept embeddings that are similar to the real ones.
So it's like taking a clear image, blurring it more and more, and then training a model to unblur it. And by learning to unblur images, the model learns how to generate new images from scratch.
Exactly. And they found that these diffusion-based LCMs, which they called diff LCMs, actually performed quite well, often outperforming the base LCM on those evaluation metrics we talked about.
So using these more advanced training methods really seemed to pay off. What about that zero-shot learning capability? Did that pan out in the experiments?
Oh, yeah, that's where things get really interesting.
Tell me more.
They tested their larger 7 billion parameter LCM, which they called two-tower LCM, on a data set called XLSUM, which is a collection of text summaries in 45 different languages.
Okay, 45 languages, that's a pretty good test of cross-lingual ability.
Right. And what's really remarkable is that this LCM, which was primarily trained on English text concepts, outperformed a similarly sized version of Llama 3.18b-IT, which is a state-of-the-art LLM that was trained on a massive multilingual data set.
Wow, so it's not just that it can handle other languages, it's actually outperforming models that were specifically trained on those languages.
Yeah. Exactly. And this wasn't just on a few cherry-picked languages. The LCM outperformed the LLM across many of the 45 languages in the XLSUM dataset, including several low-resource languages like Southern Pashto, Burmese, Hausa, and Welsh.
Low-resource languages, meaning languages that don't have a lot of training data available.
Right. And for these languages, the performance difference was even more pronounced. It really highlights the potential of LCMs to democratize access to sophisticated AI tools for communities that have historically been underserved by AI research and development.
So this could be a game changer for things like machine translation, cross-lingual information retrieval, or even just being able to communicate with people from other cultures more effectively.
Exactly, and it's not just about language. Remember, Sonar can also handle speech and potentially other modalities. So you can imagine a future where you could use an LCM to translate between spoken languages, generate captions for videos, or even control devices with your voice in any language.
That's pretty incredible. So we've got zero-shot generalization across languages, but did they test any other capabilities?
Yeah, they also did some experiments with instruction tuning, which is basically fine-tuning a pre-trained model on a data set of instructions and examples to teach it to follow instructions and generate text that's relevant to the given instructions.
So more like the chatbots and text generation tools that we're all familiar with.
Right. And for this, they used a data set called Cosmopedia, which is designed to test a model's ability to generate coherent stories and follow instructions related to the story. And they compared their instruction-tuned LCMs to a smaller version of Llama, which was specifically designed for instruction following.
And how did they stack up?
Well, the LCMs achieved competitive results in terms of capturing the main points of the story and maintaining consistency in the narrative, although the Llama model still had a slight edge in terms of fluency, which is something that LLMs are typically very good at.
So it seems like there might be a bit of a trade-off here, right? The LCMs are maybe sacrificing a bit of fluency in exchange for this incredible zero-shot generalization ability and this ability to reason at a higher level.
That's a good observation, and it's something that future research will need to explore further. But even at this early stage, the results are pretty promising.
Yeah, for sure, especially if you're working on tasks that require more than just fluency, like tasks that involve reasoning, problem solving, or understanding complex information.
Exactly.
Speaking of complex information, their researchers also mentioned something about the fragility of these sonar embeddings, right? What was that all about?
Yeah, that's an interesting point. They noticed that certain types of text, like those containing a lot of hyperlinks, code-switched language, or numerical data, tended to produce sonar embeddings that were more susceptible to losing their meaning if they were even slightly perturbed.
Perturbed?
Like if you change a few of the numbers in the vector, the meaning of the sentence can get lost more easily for these types of text.
Yeah.
It's like these embeddings are more fragile for these concepts.
Interesting. So it seems like the way we format and structure information can actually impact how well these concept-based models can understand it.
Exactly. It highlights the importance of careful data preparation and potentially even developing new techniques for embedding certain types of information more robustly.
So garbage in, garbage out, as they say, even with these advanced models.
Right.
Now, we talked about efficiency earlier. LLMs can be real resource hogs, especially when you're dealing with long texts. How did the LCMs perform in terms of efficiency?
Well, their initial findings suggest that LCMs might be more scalable than LLMs for tasks involving longer contexts, especially when those contexts consist of longer sentences. Because they're processing shorter sequences of these concept embeddings compared to the long sequences of tokens that LLMs have to deal with, the computational cost doesn't increase as rapidly as the input length grows. However, for very short pieces of text, a traditional LLM might still be more efficient, so it really depends on the task.
So if you're working with really long documents or you need a model that can understand and reason over longer stretches of text, LCMs might be the way to go, but for shorter tasks, LLMs might still have the edge.
Yeah, that seems to be the emerging picture. And on top of all of that, they even started exploring ways to incorporate explicit planning into these LCMs, which is really exciting.
Planning? What do you mean by that?
Well, they introduced this idea of a large planning concept model, or LPCM, which is basically an LCM that's been trained to not only predict the next concept embedding, but also to predict a kind of abstract plan for the following concepts.
So it's like giving the model a high-level outline of what it's supposed to generate before it starts generating the actual text.
Exactly. And their initial experiments suggest that this could potentially lead to more coherent and structured long-form text generation.
So not only are they understanding language at a higher level, they're also starting to think ahead, to plan out their output in a more strategic way.
Yeah, and that's a really promising direction for future research. Imagine being able to give an LPCM a high-level goal, like write a persuasive essay arguing for or against this particular policy. And the model would not only be able to generate the essay, but it would also be able to plan out the structure of the argument, anticipate potential counterarguments, and present the information in a clear and compelling way.
That would be a huge leap forward in terms of AI-powered writing.
It would.
Well, this has been an absolutely fascinating deep dive into large concept models. So just to recap for you, our listener, we've explored this brand new approach to language modeling that shifts the focus from individual words to these higher level semantic concepts.
And the key to this whole approach is this incredibly versatile system called sonar, which can represent the meaning of sentences in a language and modality agnostic way, opening up all sorts of possibilities for cross-lingual and even cross-modal communication.
Exactly. And the researchers have shown that these LCMs have some really impressive capabilities, including this amazing ability to generalize to new languages without any specific training, the potential for more efficient processing of long contexts, and even early signs of more structured and planned text generation.
It's still early days, but this research is definitely pushing the boundaries of what's possible with AI, and it's got a lot of people excited about the future of language modeling and AI in general.
And for you, our listener, hopefully this deep dive has given you a good understanding of what these LCMs are, how they work, and why they're such a big deal. We know you're interested in the cutting edge of AI, and this is definitely one to keep an eye on.
And if you want to delve deeper, the researchers have made their code publicly available on GitHub, along with the code for the Sonar embedding system. We'll include links in the show notes.
Now, as we wrap up, here's a thought for you to ponder. If AI models can truly understand and generate ideas at this conceptual level, independent of any specific language, what incredible new possibilities could this unlock? Could we see a future where language barriers are a thing of the past, where information can be seamlessly shared and understood across cultures, and where creativity and expression are no longer limited by the constraints of language? It's a pretty profound question to consider. Thanks for joining us on this deep dive.
Yeah, thanks for listening.